Is this what we're doing?
Okay. So in this problem, we're trying to move a compound X from cyclohexane to water, and we're given 3 different temperatures to work at with 3 different equilibrium lines. So let's start by labeling our regions on the graph. So can anyone tell me what part of this graph the water is supersaturated with X? So there's too much X in the water. Come on, you guys had to come up with this to do the problem. Which side of the equilibrium lines? Above it or below it?
Below.
In between the axis and A.
Above it. This side will have way too much X in the water. So where does that leave? Where's the cyclohexane supersaturated with X? Below. Okay. Keep that in mind when we're doing this. Okay, so let's start by looking at, for a given weight fraction of X in cyclohexane, we'll say about 5 weight percent, how much can the water absorb at each one of these temperatures? Right? So where would I have to move on this graph to look at how much water is absorbing at this point? Well,
you can draw the line straight up and wherever it intersects with the temperature, and that's where it is.
All right, and then once it intersects, where do I read off? So I draw, you said draw a line straight up, and then I get points here, and then what am I reading off to figure out how much X is in the water? Go completely horizontal, right. Okay, so based on this, it looks like if we're operating at TA, we're going to get much more X out than if we're operating at TC. All right, so either if we have the same flow rate of water at each one of these temperatures, we're going to extract more X out because we're going to get a higher concentration here. Or if we're just looking for a given fraction of water or fraction of X out, we can use a lower flow rate since that water will be more effective in taking X out. So here this is saying that temperature A is the most effective. All right, so there's a couple different ways to do it. So let's look by actually drawing out this absorption. So we're going to start by drawing an operating line, like that. And let's just say arbitrarily that we have 1% X coming out of the cyclohexane. We can count off stages. Let's do it for TA. Draw it down. So it's saying if I want 1 weight percent of cyclohexane coming out, I can only put in a cyclohexane with about 2.5 weight percent. So this is going to be kind of my recovery of X that I'm getting out of the water. Okay? So we can do the same thing for temperature C. Right, and this absorber has 4 stages. So we can see that with just a few stages, we're going to be way off this graph, and we're going to get a huge recovery of C. So this is saying that temperature C is going to be a lot better at extracting X. But previously we just said temperature A. So which one's better? A or C? Which analysis was correct? Just based on the previous slide, we said that temperature A was by far better. And now I'm saying temperature C is better. What do you guys think? Well, what did you guys say? Which temperature did you pick as the one that was better? You guys are finished with the problem, right? Which one did you guys pick?
We picked A.
A. So you guys think A? Does anyone else think A?
Yeah.
Why? Why do you think A?
Well, because you should have more cyclohexane, and you should have more X in the water, like by the graph.
Okay, so that means something about this was wrong, right? What did I do wrong in this example? Dan?
Operating line?
What's wrong about the operating line?
I'm not really sure, but there's got to be something wrong with the operating line.
Well, shouldn't the operating line be different if it's at a different temperature?
No, not going to be different for different temperatures. Rachel?
For the operating line, you start with no X at all. Like your weight fraction in both of the streams, you start at 0, which means there's like no X in either stream.
Okay, so we could be starting like up here. So that's not it either.
Does your operating line have to end at one of the equilibrium lines? Like, no.
That's not what I'm looking for. Almost got it.
Right now, aren't you like extracting X from water?
Yep. So where should this operating line
Should be
really
on
be?
the bottom.
There you go.
You should try to do the opposite.
All right. So right now we're saying that we're operating in this region where we have too much X in the water, but we don't have too much X in the water. We have too much X in cyclohexane. So we need this operating line to be in this regime. If we try to separate X from cyclohexane to water by operating in this region, we're actually going to go backwards. We're going to take the X from the water and put it into the cyclohexane, which is not what we want. This is wrong. So we need the operating line to be in this region. And now if we count off stages for C, and for A, you can clearly see that the recovery at temperature A is going to be much higher than the recovery at temperature C. Right, so when you're figuring out where your operating line needs to go, it is really helpful to label these regions. Right, and it's always whatever the thing is, what it's rich in. So this X is cyclohexane is rich in X. So that means our operating line has to operate in that regime. That's a neat little, just simple way to tell. Any questions? All right, we need to get started on the next problem.